All right, so good morning. I want to show the spreadsheet here. So the schedule today will be Ryan Buss first, and Katie second, and then John Shield, the third one. I make each one of you the co-host. All right, so everyone have to score these presentations using this spreadsheet. So it will be really easier for me if you use the same spreadsheet, because I can just copy and paste. All right. So Ryan, are you ready?
Yep, I sure am. Let me.
Okay. Okay, so I'll give you 10 minutes, and then if there's an extra time, you can continue until 15 minutes. All right. And then otherwise, I will just mute you. Okay. After 15 minutes. Thank you.
That seems perfectly fair.
Yeah.
All right, my name is Ryan Butts, and we did our project on some transparent solar panels, how they work, and a cost analysis and energy analysis of a building if we were to implement them at Auburn. My team was supplemented by my undergraduate assistants, Jamarius, Zach, and Keenan. So I'll just get started. So I'll give a brief synopsis of some solar panel technology, and then we used Horton Hardgrave Hall as our case study because they've got a lot of windows, and we felt like there'd be a lot of bang for your buck with implementation on that building in particular. So this is a basic substrate layup of a solar panel window. A couple things that make it different are the UV reflectors and the transparent electrodes. I also thought it was interesting that these optional AR coatings, so it's anti-reflective, so they really want to prevent any energy that could be absorbed from reflecting away and not being usable. The other thing that I thought was very interesting about the overall technology was the panel acts as kind of a bandpass filter. So the visible light spectrum you need to pass through so that we can use it to see. But if you look at the gray graph in the back of these graphs here on the right, you can see that there's a lot of energy in that visible light. And of course, obviously in the ultraviolet as well. We all know that from our time spent down at the beach. And the studies that we saw also had a lot of emphasis on the infrared, which I think might be easier to capture, which is why they talked about it a lot, but the energy density really seems to be very poor in the frequencies that are below the visible light spectrum. So this is just a quick comparison where you can see a conventional panel here on the bottom left versus a transparent panel on the top right. Obviously, the transparent panel is a lot more challenging to make. You lose a lot of that high energy dense spectrum that you're trying to pass through. So the overall efficiency is much worse than a conventional solar panel. Also a lot more expensive, and we'll talk about that here, I think, on the next slide. There we go. So part of it too is how much of that light you let through. So there are basically two types of transparent or window panels. Semi-transparent, which I mean is looks like a tinted window, and they can be up to around 7 to 12% efficient, and they're a lot less expensive. If you want a fully transparent window, it is a lot more expensive and way less efficient. Researchers expect this to improve greatly, and I've seen some other studies where even in the past couple of weeks while we were working on this, that I think they were in China or South Korea, where they got a transparent solar panel to be a lot closer to 7 to 12% than this 1%, but it's not something that is really attainable in a way that we could install it today. By comparison, I think we talked about in class that a conventional solar panel typically runs around the 25% efficiency rating. So you're looking at orders of magnitude worse. The other thing that was cool is I was looking at a study, and they really focused on using the tint as well to help lower costs. So obviously tinted windows keep your car cooler in the summer, can also be used in buildings. The one that I thought was really cool was that they had red-orange tinting on some greenhouses, and that apparently made a bunch of leafy green vegetables grow better, which isn't a side effect that I had ever really thought about, but I thought that was kind of cool. So the case study, the idea for this project came to mind when I was looking for a smartwatch, and Garmin makes a watch that they implement a transparent solar panel into the face, and it adds them an extra about 22% increase in the battery life of the watch, which obviously a watch uses a lot less power than a building, but that's a very substantial increase in your usability. So we thought, what kind of impact would that have if we were to put it on a building here? So this is already being done by a fair number of companies. Heliotech, I believe, is out of Germany. Onyx Solar is American, I believe. And we used available information from these companies, as well as using the information we learned in class here and the installation tables to do this study. So the first part is my researchers went out and figured how much windows we were working with. So as you can see, typically when we talk about these kind of things, we're talking south-facing windows to get the most sun. I know we talked in class a lot about that. Most of the windows on this building are on the east and west side. I assume there's also a bunch on the north side, but that doesn't really help us a whole lot in this application. Using the costs that we found in those previous studies at 40 square foot for a transparent window, or $8 a square foot for a tinted window, you're looking at closing in on $1 million if you want to replace them all with transparent windows, or about $165,000 for the tinted style. And just to note, this is only the solar panel windows. It doesn't include installation, power converters, wiring the building, incorporating with the utilities. That would all be extra. It'd probably end up costing 25–50% more, if not more than that. So we use the installation tables from Appendix E, had to interpolate because we had a 30-degree and a 35-degree table, and we used some interpolation to estimate what we have here at about 32.6 degrees latitude. And we found that our transparent windows could get us about 15,000 kilowatt hours a year, and our tinted windows about 150,000 kilowatt hours. And that goes back to what was shown earlier with the efficiency of the transparent window being about 1%, and we used 9.5% because that's right in that 7 to 12% efficiency that the other studies were citing. And this is a table that shows how it looks across the year. One thing that's kind of interesting is, as you see, May, June, July, sun's higher in the sky. Since we have vertical 90-degree windows, we're getting less direct sunlight, so we get better efficiency on the winter months. And this table just kind of shows all of that. I forgot to put on the labels, but these lower graphs are, the blue one is the south, and the black one is the east, and the gray one here is the west. So yeah, in the summer you can really see the south-facing windows really aren't as effective. All right. So to put this into some perspective, this is a graph from this site here that's provided by Auburn. It's a cool site. It actually shows you the energy and overall utility consumption of pretty much every building on campus, even down to like the football stadium. One thing to note about this one is this is for last year and this year. Obviously, when we pulled this, it's April still, so we don't have the full April data for this year, and we've been all over the map. So we use the numbers from last year as kind of a guideline. And oops. So if we were to implement this with transparent windows, we're looking at being able to supply 0.5% of the total energy expenditure based on that last table. And if we were to use the tinted windows, we could get just a little bit above 4% across the entire year. Some months are better than others, depending on how much energy we're able to produce in that month based off those insulation tables and how much energy we use, which depends a lot on how hard the HVAC systems have to work. So the financial impact of that, this is based off of the Alabama Power, where on their website they provide different utility rates based on different sizes of loads, from commercial to residential, everything in between. We just use this. I would imagine that Auburn, being a very large load on their system and being a public university, they probably have a special deal that is slightly different than this, maybe slightly more advantageous for Auburn, but I don't know what that might be. But using this price per kilowatt, this is what we found would be the overall impact of implementing the solar panels from a financial standpoint. So we're looking at about $5,000 down to $500, depending on which ones you use. So to summarize, Horton Hargrave Hall uses a lot of energy. Based off of that, we're estimating about $150,000 a year, and that's about $10,000, just over $10,000 a month. That's a lot. I think it's hard to really understand that from a person who lives in a 1,000 square foot apartment, just how much that is compared to where I live. That's 100 times as big. So it stands to reason they use a lot more energy, and there's a lot more going on inside. That being said, if you have transparent windows and it costs nearly $1 million to install and you're only getting back $500 a year, you have a really poor payoff period. And with tinted windows, you get a much better payoff period, but it's still not making a whole lot of money. So in conclusion, transparent and partially transparent solar cells may be effective someday, especially in locations where you don't have places to put conventional solar panels. And just buildings use a lot of energy, and making things more efficient and lowering that energy may be more cost effective than trying to increase your energy production. And as this all develops, costs will decrease, and I think we'd expect to see this be a relatively common solution throughout the world. And that's the end.
All right, thank you very much. So we don't have time. Perhaps we should move on to the next one, which is that Sriya? Or let me see. Who's the next one? Katie, maybe, right?
Yes, that's
Yeah.
me.
All right.
Okay, so today I will be presenting our project, Decentralized Micro Hydropower, Sustainable Energy for Remote Communities. And my team was comprised of myself, Katie Day, Martin, and Rosie Harris. Okay. So to start off about why this is the project that we chose, micro hydropower systems provide sustainable energy for communities that lack access to centralized grid systems, which makes them ideal for places like small towns or remote locations, or even if you're just in a place where you want to have an off-grid application. And they do this by harnessing the kinetic energy of flowing water and making it into electricity while trying to minimize the environmental impact. Micro hydropower is specifically advantageous because it operates continuously, unlike solar, which is not as helpful when the sun is down, or wind, which isn't always blowing. It also typically requires lower infrastructure costs compared to traditional large-scale hydroelectric projects, making it potentially feasible and scalable, which is what we're trying to investigate here. The goal of the project specifically was to see if we could find an optimal location for micro hydropower installations in the United States, talk about the design of what an efficient and cost-effective system would look like, analyze that for economic feasibility, and then kind of talk about and evaluate the social and economic impacts of installing one of these systems. So we started off with a literature review. It's always good to get kind of lay of the land of what's going on. And these small-scale hydropower systems are widely considered to be one of the more effective and environmentally friendly energy production methods that we have available right now. If you want to go like all the way back in history, the implementation started with the water wheel in Asia and Europe. And then as society progressed with the Industrial Revolution and all of those types of things, we ended up developing things like turbines and pumps. And now modern hydropower systems are used all over the world, particularly in some of the more mountainous regions of the Southeast in the US. For modern micro hydro systems, they typically have a maximum power output of about 100 kilowatts, and that's produced by small dams, turbines, pumps, things like that. But they do not store large amounts of water and are not meant to power large communities, which is a key difference between some of the dams that we know up on Lake Martin and places like that. In some of the more specific case studies that we've talked about, we were looking at the constraints of what existing micro hydropower systems use. So things like the flow rate is typically greater than or equal to 0.5 meters cubed per second. The head height is greater or equal to 2 meters. And all of them, try to minimize ecological disruption. That's kind of the whole point of renewables, isn't it? Some brief standards and codes and things that are applicable. Just kind of doing a brief evaluation of the different regulatory bodies and things that you would need to abide by when you're installing one of these systems. You've got OSHA, right? Your 1910-219 is your machine guarding for rotating equipment. This is pretty applicable across most power generation. You've got IEEE 1547, which is how you interconnect distributed resources to power systems. And then obviously you have your NEC, National Fire Protection, and that's NFPA 70, which is Safe Electrical System Design. And obviously we would want to follow all of these things to ensure our worker safety, electrical safety, grid compliance, all of those things that make society run safely. So let's get into site selection a little bit. One of the things that we were determining when deciding where to place our micro hydropower, we wanted to keep in mind the flow rates, the turbine sizes, and then the geographical features that could have effect on the efficiency of the system. Most specifically, we were taking into account flow rate and head height. And then we also wanted to try and pay attention to inconsistencies of like water availability. Is it a location that doesn't have water year round, which is typical in the West? And the amount of sediment that would be pushed around by the turbine, environmental regulations, all of those things. So the two locations that we picked that we thought could benefit from this technology in the US would be in remote regions in the Oregon, Washington area or in the Andes Mountains. Oregon and Washington have a lot of water supply that also has a lot of elevation changes due to the mountain ranges out there. So that would allow for higher head heights and maintaining stable flow rates. And you could place these micro hydropower systems in regions of small local towns that are kind of spattered across the areas. You could also place the system in the Andes Mountains, which would result in high head heights with a relatively stable water supply. And this is for if we were wanting to place it outside the US near the Amazon. And this one would be a particular interest because there are many small and rural communities in those regions that still don't have electricity or consistent electricity. So implementing micro hydropower there with mild or minimal ecological disruption would be ideal for those communities. So then when we get into the actual system design, we wanted to consider how to take advantage of the resources that already exist in these areas, whether that be in the US, in Oregon and Washington, or whether that be abroad in the Andes. We pretty much immediately decided on using a run-of-river design so that there's no dam. This allows for continuous flow and you're not backlogging the system, ruining the water supply, things like that. They are also quicker and cheaper to build than the large dams that we see and study. But the important downside to note about these is they lack substantial storage. So they produce less power and they're not nearly as flexible during dry seasons or if there's peak demand and things like that. Many of these run-of-river sites, while we want to maximize head height, are considered low head environments so that the drop from intake to turbine is relatively small. So this is, under about 20 feet. And then some of the components that we specifically wanted to evaluate and include in our design, we've got the penstock, which is the pipe that actually carries the water from the intake down to the turbine and then converts the head into water pressure and then directs the flow and all of those lovely things. Obviously, you need the turbine itself. It's kind of the heart of the system, and it's what causes the shaft to spin and thus generate electricity. These are typically in microhydro designs pretty small, but are designed to operate continuously. Then you need the generator, and that's what converts the mechanical energy into electricity. And most of these systems would either use synchronous alternators or induction generators to produce your AC power. And we would also include a built-in voltage regulator to regulate the output. And then as far as control systems, we would use an electronic load controller to automatically balance the load and prevent any further prevent any frequency fluctuations or anything like that by diverting excess power to dummy loads. And of course, we would want to consider battery storage because you don't have the storage capability due to water storage of the large dams. Ideally, we would want to look at using LiPo batteries or something similar, but of course, you need to take into account that those are expensive and also not particularly great for the environment. So you need to be very particular about how you store them, make sure they're not at risk for exploding, catching fire, all of those lovely battery things. So now we get to the economic analysis, and the general overview of this is it really depends. It is highly variable based on starting costs and actual location selection and what the weather does. Is there going to be a drought and things like that? But based on what we kind of analyzed and considered, your startup cost on the low end could be as low as $65,000 or so, could go all the way up to $500,000. Again, it just kind of depends on what components, scale, location. Permitting is wildly variable depending on the location and the regulatory bodies of where you are. because the startup cost is so variable, the payback period is also incredibly variable, and so is your ROI. But to get an idea of kind of low end and high end estimates, on the low end estimate, if your startup costs are $205,000, then you come back with a net annual savings of around $20,000, which means your payback period is about 10 years. So that's pretty good. But then, especially if you're considering a 20-year project lifetime. But on the high end, if your startup costs are closer to that $500,000 number, then your net annual savings would only be around $3,500, and your payback period is then about 132 years, which is obviously much less optimal. This variability also leads to differences in your ROI, where your net savings on a low end estimate, or your ROI on a low end estimate could come back at 93.66%. Or if you had a super high initial cost, you actually come back at losing 84.78% on your ROI. And so that is not ideal. Basically, all of this is to say that microhydropower can be feasible and economically viable, but you do need to have careful site selection to make sure that you know what you're doing and you're not about to blow a bunch of money. There's also different government plans to help you fund these things if it's something you're interested in. In the US, you have the Rural Energy for America, or REAP program, which is administered by the USDA and offers grants for up to $500,000 for renewable energy systems and can cover up to 25% of the cost of the system itself. The DOE also has funding for water-based projects, so this would fall under that. And if you're looking abroad, say you want to build this in the Andes, you would have international funding programs like the International Renewable Energy Agency, or IRENA, and the World Bank, who offer grants and subsidies and things when you're installing renewables in developing countries. For the environmental and social impact, again, we're looking at low impact design and the community benefits. And the way we looked at this is, for the environmental impact, we would implement fish ladders and fish passage so that fish can pass through, and then our system would not impede the migratory patterns of fish, allowing fish to move upstream past the turbine. And then downstream passage is facilitated by screening the intakes and providing bypass flows for said fish. And then run-of-river projects specifically minimize sediment by avoiding large reservoirs, but the intakes can still accumulate sediment. We also would minimize physical footprint, things like that. As far as the community benefits, you've got local jobs for when you're actually building. You would have stable electricity. And then you also have just the economic growth that comes with more stable electricity. In conclusion, microhydro can offer affordable, sustainable power, but you do have to be intentional about how you install it. And the status of this project specifically, if we were to continue going forward with it, other than just the initial analysis, we would begin finalizing design feasibility. For next steps of things that you could do, you could look at technology adaptation to reduce cost. You could standardize design templates. You could integrate monitoring systems. A lot of work needs to be done in policy and funding alignment in a broader global scale. And obviously, you should focus on community-centered development. Thank you. Questions?
So if you have any questions, looks like we have 2 minutes. Is there any 1 or 2 questions? All right. So if you have any questions, you can send to email to Ryan as well as to Katie. And I'm sure that you can find their email address. So let's move on to the next one, which is John Shield.
Hey, good morning. Can you hear me?
Yeah.
Okay, great. Let me get. Can you see my screen?
Yes.
Okay. Good morning, everyone. Apologies if I speak quickly. Just got a lot of slides to get to today. My name is John Shields. I was part of a team with Jake, Trevor, Gray, and Andrew, and our project was on mining the sun. So a quick overview, introduction, we'll go over the power, solar energy, a case study, and then conclusions. So introduction, what is mining the sun? It's using solar power to mine Bitcoin. So for anyone who's not really familiar with Bitcoin, essentially it boils down to the process of using energy to find a number that satisfies a condition. And a little more detail on that is you have these nodes, which are computers, specialized computers that run Bitcoin, perform a hashing proof of work. And the main takeaway is that takes a lot of power consumption. So once those transactions are gathered into a block, they're hashed to find a difficulty level. And then when a solution is found, is broadcast over the network, and then payments are collected. Then the next block is generated, and so on and so forth, creating a blockchain. The main takeaway from this is that it takes a lot of power. So how does it relate to renewable energy? Bitcoin mining rigs can be set up near power plants. About 67% of US energy is wasted, and this is mostly to do with transmission and just low demand during generation periods. So about 70% of US energy is wasted, and you can set up these mining centers near power stations in order to buy that wasted energy for cheap. It's often, so Bitcoin is often seen as a waste of energy, but the main takeaway here is it does have real utility as money, and it uses less power than other things like gold mining or even video games. Like Katie was saying, it can also be used to justify the creation of a grid to bring power to remote areas. And as you offload Bitcoin mining, you can onload people who pay you for that same power. Okay, so a little overview of our system here. We'll have our solar panels connected to a controller, which in this case is going to be inside of our inverter. We're going to have a battery bank, and then that is going to go to the load. In our specific case study, we did not connect to a meter or to the grid, but that is a possibility as well. So to start us off, the miner we're going to be using today is, sorry, typo there, S21XP. It's got 270 terahashes per second and draws about 3,800 watts. It has fans, but needs AC and ventilation. And the power consumption per year is about 33,000 kilowatt hours per year. It's got pretty good efficiency of 13.5 joules per terahash. Okay, so looking at our solar energy, we have about 5 hours of sunlight a day here in Alabama. That's generous. As you can see on the map, it's more like 4.5, but we'll just say 5. That gives us 19.1 kilowatt hours in that 5-hour period. And then the 19 hours of night or no sunlight gives us 72 kilowatt hours. Add those together, divide by the efficiency of the system, which we're going to assume is 85%, gives us 108 kilowatt hours a day. With that 5 hours of sunlight a day, we need about a 21.64 kilowatt system. We're going to round that up to 22 kilowatts. And for most of these calculations, we are very, very conservative. Because when it comes to solar, you just need to be conservative. So to meet that 22 kilowatt system, we have these Solaria solar panels. They are each 370 watts. And so 60 of them gives us 22.2 kilowatt system at $420 each. It's about $25,000. And you can see on the top right there, we have a running total, which is at this point, the solar panels plus the miner. So that 22.2 kilowatt for 5 hours gives us 111 kilowatt hours a day, and we needed 108. So that's pretty good. The efficiency of these specific solar panels is about 20%, which is fairly good for other solar panels in the market. So for energy storage, we're going to use these batteries by LG. They're 6.5 kilowatt hours. We're going to need 12 of them to get our 74 kilowatt hours a night. And we needed 72.77 kilowatt hours. So we're right above the amount of energy storage that we needed. These are pretty expensive at $4,500. And at this point, this is the most expensive part of our system at $54,000. Ideally, you'd want 2 to 3 days of storage for a solar panel system like this, but for this specific case study, we're only gonna look at 1 night storage. For our inverters, we're gonna use 2 of these hybrid inverters at 7.6 kilowatts, 3 strings of MPPT technology, gives us a 14.9 kilowatt system. That's plenty of headroom, and our DC to AC ratio is 1.34. We're going to connect our strings up 10, 10, 10, 10, 10, 10. Pretty straightforward, and the total cost for these 2 inverters is going to be about $10,000. So other parts we may need, racking and mounting. As Jack said, good thing we went with the fixed axis, it sounds like. So these are fixed axis racking, wiring about 1,500, installation, say 5,000, and then taxes, call it 10%, gives us a total price of $110,000. And there you can see a summary. We use a free online resource called Open Solar to plan out this project. And there's also a nice graph for April showing our power generation, storage, and consumption for the month of April. Okay, so for our case study, we're going to be looking at Brown Hall. There was a nice roof facing south, which is what we want. And Auburn, Alabama has on estimated 208 Sundays a year. This specific location has really, really good shading data shown there down below. And the purple lines you see there are the strings of solar panels connected to each MPPT inverter. Once again, this data was taken from Open Solar. Okay, so going back to our Bitcoin mining, the network hash rate, just to get our profit margin, is going to be about 841 exahashes, which is 841 million terahashes. Our hash rate is actually 270 terahashes, giving us a mining share of that really small number, 3.21 e to the minus 7. Block rewards right now are 3.125 Bitcoin, averaging 10 minutes is about 144 blocks a day. Price of Bitcoin is about $94,000, which means about $42 million is mined a day. Our share of that is $13.50 a day for about $5,000 a year, assuming we run 24/7, 365. And just a small note, usually people don't calculate their profits like this. This is a very quick and dirty way to calculate them. Usually people join mining pools where they have more consistent payments, but there are fees. So for our cost analysis, we're going to put that into the spreadsheet, table 6.6. Here you can see our system costs, rebates, final costs, and down payment. Our down payment is going to be 20%. And here I'm showing on line 31, instead of buying power to run this, we are going to be using the profit from the miner as the utility cost offset. So that's what line 31 is showing there. And that gives us an internal rate of return of 10% and a net present value of about $10,000. So will it work? Probably. Is it worth it? Probably not. Now, $110,000 cost, $10,000 net present value, about a 10% return. It's not great, even compared to like the S&P 500, but there are many other things to consider. The first is that the next halving is in 2028, so 1.5625 block rewards will happen in 2028, reducing our profit margins. System degradation. If you put it on a roof, maybe Brown needs a new roof in 5 years. That's something to consider when you attach all of these 60 panels to the roof. Also, PV systems only expected to last about 20 years on average. The batteries can last even less than that. And our break-even point is at 23 years. So you're kind of cutting it close as far as when you're going to be breaking even. And our analysis was as far out as a 30-year loan. So that's something to consider. We could change location to somewhere more sunny like Arizona, which has on average 365 sun days a year. Maybe we could find some promotional incentives, brand endorsements, spokesperson for your neighborhood, maybe get some money that way, or Alabama tax credits. I found some that are about $3,000 for solar energy, but I did not include them because it wasn't very clear how you got those. We did include the 30% federal reimbursement or rebate in our cost analysis, since that helps out a whole lot. Like I mentioned, you could connect to the grid to buy or sell energy. If you're generating more energy than you need, you can sell some back or buy some if you need it. Also, mining is scalable, so all of these profit margins, costs, everything is pretty much one-to-one scalable. So if you have a lot of money that you want to invest and you see this as a good idea, then 10 miners is better than one. Like I mentioned before, it can bring a grid to a remote area if it justifies the creation of the grid with a break-even point of 23 years. But in that time period, you can have people on load and you can offload the mining and replace it with paying users. Also, something to consider, the price of Bitcoin increasing. Ran the same calculations at $109,000, which was the peak back in January, and that would make about $5,700 a year. So with that concludes our project. And are there any questions?
Yeah, I have a questions about, the logic behind using a battery with this in Brown Hall, right? So if you remove the battery, you have removed significant capital cost. I wonder if you consider that.
So for Alabama, we're looking at like 5 hours of sunlight a day, and that's even like 208 Sundays a year. So you'd really want a good amount of storage, just not only for the night, but if it's rainy or cloudy.
Nice. So the process of computing this Bitcoin here takes, you cannot have a downtime or what?
Correct. So this profit calculation where we got to our $5,000 was assuming we run 24/7, 365. Any downtime at all is going to cut into that profit.
I see. Wow, this is a very challenging issue here. Yeah, I didn't realize that, actually, this is consume a lot of electricity.
Yes, and that's, go back to this slide. 3.8 kilowatts, and that's even before you include, maybe you want to increase a little bit of efficiency by adding a cooling system, which could be another 200 watts. And then extrapolated over the course of a year, 33,000 kilowatt hours is a whole lot.
I see. Interesting topic. There's a professor here is teaching Bitcoins, and have you talked to him? Dr. Reeves? Dr. Reeves?
Yes.
Oh, you did? Okay.
Yes.
Okay.
Yeah, if there's no other questions, thank you.
Yeah, thank you very much. All right, so any other questions for the presenters today? Again, anytime you have any questions, you can just email them. And just a reminder, so all the presenters have to submit 2 questions to be considered for final exam. Okay, and please use this spreadsheet available. It will make it easier for me to move from your spreadsheet to mine. All right. Well, otherwise, I'll see you in the final exam. So thank you very much. Bye-bye.